As programmers, we've probably written a line like this hundreds of times. You ask for memory and you get a pointer back to memory. We're told in our CS classes that this memory comes from the heap. But there's just one problem. The heap you're probably thinking of and the heap the OS keeps track of aren't really the same. This one word is hiding two completely different machines underneath it. So let's pull them apart and see what's inside. Every process has its own private map of memory, an address space. The OS tricks each process into thinking it has the whole machine to itself. How exactly that works is a topic for another video. Today we only need to know one thing. This address space is split into different regions. Your code sits here, your global data here. Then comes shared libraries and a few gifts from the kernel. Of course, we can't forget the stack. The kernel tracks each one of these regions in an entry called a VMA. You can even read the list of VMAs yourself. All these regions are important, but today we're only focusing on two. The stack and the heap. The stack is elegant. Every time a function is called, it finds space for local variables instantly. When the function returns, this space is automatically usable again. That automatic cleanup is why it's so fast, but it's also why it's so restrictive. Look what happens when you try to keep something past its function call. The memory's gone, it died with the function, and this results with undefined code. If you want memory that outlives the function, you'll need a way to decide when it's freed. You need to store it somewhere else. There are two ways your process can acquire memory. Both requires a little help from the OS. Let's investigate what you probably already know. This is the classic heap, and it all works with one single line. Right above the global data, there's a boundary called the program break, and we consider everything between the heap. When your program needs more memory, it gets the kernel to budge the line up a bit. This is done with the brk system call, pushing the break higher, which grows the heap. Now that there's more space to work with, the program's allocator can carve little objects out of it. That's what the OS considers the heap. But this heap has an innate problem. If you free something from the middle, you're left with this hole. Free more objects and you're left with lots of total space, but not much usable space. This is fragmentation. Fighting fragmentation is the biggest job of a memory allocator and what makes them so complicated. But even the best ones can only minimize this problem. But it gets worse. The program break only moves at the top, so even if a huge chunk is freed from the middle, it can't be returned to the OS. The user process is holding it hostage. But how exactly do we solve this? Let's take a look at our other option, our other heap. Instead of growing one shared region, we can ask the kernel for whole new independent regions at a time. This is done through a syscall called mmap. Because they're standalone, when you're done with it, you can just hand the entire region back to the OS. There's no holes, no fragmentation, and no hostage memory. This flexibility isn't free, however. It's a whole system call and a very expensive one at that. The OS always has to give you whole pages. Asking for a few bytes will still result in 4,000 bytes. It's great for big allocations, but not so much for small ones. So which do programs really use? The answer is both. Smaller requests often come through using brk, and larger ones via mmap. The exact threshold is implementation specific, but in glibc it's around 128 kilobytes. This means that memory that many programmers regard as a heap is actually scattered across different segments, completely different parts of the address space. Your allocator quietly picks. Small requests come from brk, which is the heap, and once a request gets big enough, it switches to mmap and gives that allocation its own separate region. Once the process acquires memory via brk or mmap, it has a responsibility to manage it efficiently in order to reduce more calls for memory and reduce its internal fragmentation. So the next question becomes, how does malloc hand you the right memory instantly, millions of times per second, while fighting all that fragmentation? That's what we'll cover next.